The morning of July 18th, 1943. Lakunai Airfield, near Rabaul, New Britain. The air is thick with humidity, and the smell of aviation fuel mixes with the scent of tropical vegetation that surrounds the runway. A group of Japanese naval officers stand in a semicircle around an American fighter aircraft, their faces a mixture of professional curiosity and something else, something closer to disbelief. The aircraft is a Grumman F6F Hellcat, pulled intact from shallow water near Munda Point just days earlier. Its dark blue paint is still wet in places where salvage crews scrubbed away saltwater residue. The propeller blades are slightly bent, but the airframe is sound. More importantly, the engine, that massive 18-cylinder radial engine, survived the ditching. Lieutenant Commander Tadashi Nakajima climbs the wing root and lowers himself into the cockpit. He's 32 years old, a veteran test pilot with over 2,000 flight hours evaluating everything from experimental prototypes to captured enemy aircraft. He's flown American Wildcats before. He knows what to expect from American engineering: robust construction, simple systems, adequate performance. But as his eyes scan the instrument panel, something doesn't make sense. The manifold pressure gauge reads up to 60 inches of mercury. The tachometer goes to 3,000 revolutions per minute. He does the mathematics in his head, the calculations every pilot learns, and arrives at a number that seems impossible: 2,000 horsepower. He sits there for a long moment, his hand resting on the throttle, staring at the gauges. Then he climbs out without starting the engine. There must be a calibration error, he tells his commanding officer. These readings cannot be correct. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But the gauges aren't wrong, and the realization of what those instruments are telling him, what they mean for Japan, for the war, for everything he's been taught to believe about American industrial capacity, will haunt Nakajima for the rest of his life. To understand why a number on a gauge could shake a man's understanding of reality, you need to understand the philosophy that built Japanese naval aviation, and that philosophy begins with a single word: lightness. In 1937, the Imperial Japanese Navy issued specifications for a new carrier-based fighter. The requirements seemed contradictory at first glance. The aircraft needed exceptional range to operate across the vast distances of the Pacific. It needed heavy armament, 2 20mm cannons and 2 7.7mm machine guns, and it needed maneuverability superior to any fighter in the world. The designer, Jiro Horikoshi, understood that he couldn't have everything. Physics doesn't negotiate, so he made a choice that would define Japanese aviation for the entire war. He chose to strip away everything that wasn't directly essential to performance. The Mitsubishi, a 6M0 that emerged from his design team, weighed just 3,704 pounds empty. To achieve this, Horikoshi eliminated pilot armor entirely. The fuel tanks had no self-sealing capability. A bullet through the tank meant fire, meant death. The aluminum skin was so thin that maintenance crews joked you could punch through it with your fist. This wasn't recklessness, it was a calculation. Japanese military doctrine emphasized that a pilot's skill and discipline would protect him better than armor plating ever could. This was the warrior tradition, the samurai ethos, translated into aluminum and steel. A true pilot didn't need protection. He needed speed, range, and the ability to outmaneuver his enemy. And for the first 2 years of the war, this philosophy delivered exactly what it promised. When the 01st appeared in combat over China in 1940, it was untouchable. Chinese Air Force pilots, flying Soviet-built Polikarpov I-16 seconds and I-15 seconds, reported encounters with a Japanese fighter that seemed to defy physics. It could turn inside any maneuver they attempted, it could climb faster than they could dive, and it had a range that allowed it to appear hundreds of miles from any known Japanese airfield. The early reports were dismissed as exaggeration, the kind of overstatement that comes from defeated pilots trying to explain their losses. But the reports kept coming, and they were all consistent. By December 1941, when Japan attacked Pearl Harbor and swept across Southeast Asia and the Pacific, the Zero had already earned a reputation that bordered on mythical. In the Philippines, over Singapore, across the Dutch East Indies, the Zero swept Allied air forces from the sky with kill ratios that seemed impossible. American pilots who survived encounters described them with a kind of horrified awe. Captain Colin Kelly, one of the first American pilots to engage Japanese fighters in the Philippines, reported that the Zero could turn inside our tightest turn, climb faster than anything we had, and stay in a fight longer than should have been possible. The mathematics of early Pacific air combat tell the story in cold numbers. In the first 6 months of the war, Zeros achieved kill ratios averaging 4-1. In some engagements, the ratio was higher, 10-1, 15-1. At the Battle of Java Sea in February 1942, Zero pilots claimed 51 Allied aircraft destroyed for the loss of just 3 Zeros. This wasn't just superior equipment. Zero pilots were among the most rigorously trained aviators in the world. Many had combat experience in China dating back to 1937. They had thousands of flight hours. They understood their aircraft intimately, every quirk, every limitation, every advantage, and they had absolute faith in their machine. Saburo Sakai, who would become Japan's third highest scoring ace with 64 confirmed kills, described the Zero in his post-war memoir as an extension of the pilot's will. In a dogfight, at low speeds where maneuverability mattered most, the Zero was unmatched. It could snap into turns that would stall any other fighter. It could loop, roll, and reverse direction with a grace that made it seem almost alive. The philosophy of lightness had been vindicated. Japan had built exactly the fighter it needed for the war it planned to fight. A short, decisive conflict where superior skill and superior equipment would overcome any material disadvantage. But philosophy, like battle plans, rarely survives contact with industrial reality. While Japanese engineers were perfecting the art of doing more with less, American engineers were pursuing a radically different approach. They weren't trying to build a more elegant fighter. They were trying to build a fighter that could absorb punishment, deliver overwhelming firepower, and be produced in numbers that would simply drown any opponent. In 1941, Grumman Aircraft Engineering Corporation began work on a replacement for their F4F Wildcat. The Wildcat was a sturdy aircraft, well liked by its pilots for its ruggedness, but it had been badly outclassed by the Zero in early Pacific engagements. At the Battle of the Coral Sea in May 1942, Wildcat pilots found themselves in a desperate position, unable to outmaneuver the Zero, forced to rely on tactics that emphasized their aircraft's diving speed and structural strength. Grumman's chief engineer, Leroy Grumman, studied the combat reports and made a decision. He wasn't going to try to outturn the Zero. That was a losing game. Instead, he was going to outpower it. The design that emerged was designated the F6F Hellcat, and it was a declaration of a completely different philosophy of air combat. Where the Zero was graceful, the Hellcat was blunt. Where the Zero was delicate, the Hellcat was massive. The empty weight, 9,238 pounds, more than twice the weight of a Zero. This wasn't inefficient. It was armor. It was self-sealing fuel tanks. It was 650 caliber machine guns with 400 rounds per gun. It was hydraulic systems that could take battle damage and keep functioning. It was a cockpit designed so that even an average pilot could survive mistakes that would kill a Zero pilot. But the heart of the Hellcat was its engine. The Pratt & Whitney R2800 double Wasp was not an incremental improvement over previous American engines. It was a technological leap that bordered on the revolutionary. 18 cylinders arranged in 2 rows, producing 2,000 horsepower at 2,700 revolutions per minute. To put that in perspective, when the R2800 entered production in 1941, the most powerful fighter engine in safe, operational service anywhere in the world produced about 1,200 horsepower. The Zero's Nakajima Sakai engine produced 1,130 horsepower. The R2800 didn't just exceed existing engines, it shattered assumptions about what was possible. The engineering challenges were immense. 2,000 horsepower generates heat that can melt aluminum alloys. It creates vibrations that can shake an airframe apart. The torque, the rotational force, was so powerful that if a pilot opened the throttle too quickly during takeoff, the aircraft could flip over. Pratt & Whitney solved these problems through brute force engineering. Advanced metallurgy using alloys that Japan couldn't manufacture at scale. Sophisticated cooling systems with oil coolers and intercoolers that added weight but made sustained high-power output possible. Manufacturing precision that required machine tools Japan didn't possess. The first production Hellcat flew in October 1942. By January 1943, they were reaching fleet carriers. By July 1943, when Lieutenant Commander Nakajima was staring at impossible gauges in a captured Hellcat's cockpit, American factories were producing Hellcats at a rate of more than 200 per month. This was the industrial reality that Japan's military leadership had fundamentally miscalculated. They had planned for a war where Japan's superior training, tactics, and initial equipment advantage would deliver victory before America's industrial capacity could be fully mobilized. They were wrong. The exact circumstances of how the first intact Hellcat fell into Japanese hands are documented in captured intelligence reports now held in the United States National Archives. On July 15, 1943, Ensign Richard Burnett's F6F-3 suffered engine failure during a strafing run against Japanese positions near Munda Point in the Solomon Islands. Burnett was part of Fighting Squadron 9, operating from the carrier USS Essex. The mission was routine ground attack against Japanese artillery positions that were harassing American forces trying to secure the airfield at Munda. Burnett made his run, fired his machine guns, and began to pull up when his engine started losing power. He did everything correctly. He tried to restart, checked his fuel, adjusted his mixture, but the R2800 was dead. Whether from battle damage or mechanical failure, the reports don't specify. What matters is that Burnett had no choice but to ditch. He brought the Hellcat down in shallow water about half a mile offshore, inflated his life raft, and was picked up by a destroyer within 40 minutes. He assumed, as most pilots did, that the salt water would destroy anything valuable in the aircraft. The Navy wrote off the Hellcat as a total loss, but Japanese observers on shore had watched the ditching, and they moved fast. Within hours, a salvage team reached the downed Hellcat. The tide was low. The water was less than 10 feet deep. The aircraft had settled on its belly with the cockpit above the waterline. There was damage to the propeller and some buckling in the wing floats, but the airframe was structurally intact. More importantly, the engine was salvageable. They transported the Hellcat to Lakunai Airfield, where the Imperial Japanese Navy maintained its primary technical intelligence facility for the Southwest Pacific region. This wasn't just a repair depot. It was where Japan's best aeronautical engineers studied captured Allied equipment, trying to understand the technical gap that was slowly, inexorably, beginning to turn the war against them. The team assigned to examine the Hellcat included Lieutenant Commander Nakajima and 3 senior aeronautical engineers from the Yokosuka Naval Air Technical Arsenal. These weren't novices. They had examined captured American aircraft before Wildcats, P-40 Warhawks, even a B-17 bomber that had made a forced landing in the Philippines. Their preliminary report, dated July 17, 1943, is clinical in its language. Aircraft weight upon measurement, approximately 4,100 kilograms empty, suggests engine displacement far exceeding previous American fighter designs. Cockpit instrumentation indicates maximum power output capability of 2,000 horsepower at 2,700 revolutions per minute. Then comes the second notation, dated the same day, and the language is less clinical. Instrument readings cannot be reconciled with known American technical capabilities based on previous intelligence assessments. Possibility of calibration error or deliberate misinformation to mislead technical intelligence. Recommend verification through ground engine test before flight operations attempted. They didn't believe their own measurements. This wasn't stupidity. It was the entirely rational response of engineers whose understanding of American industrial capacity was based on pre-war assessments and early war equipment. Everything they knew about American aviation suggested that engines producing 2,000 horsepower were experimental prototypes, not production equipment on frontline carriers. They were wrong, but they didn't know they were wrong yet. Lieutenant Commander Tadashi Nakajima was chosen to conduct the first flight test for reasons that had nothing to do with seniority or politics. At 32, he was one of Japan's most experienced test pilots. His logbook showed over 2,000 flight hours, including extensive time evaluating captured enemy aircraft. He had flown Soviet fighters captured in the border conflicts with Russia. He had flown American P-42s taken in the Philippines and Burma. He understood how to approach an unfamiliar aircraft methodically, how to test its limits without exceeding them. But according to his post-war memoir, published in Japanese in 1952 and partially translated for American aviation historians in the 1970s, Nakajima approached the Hellcat with something beyond professional caution. He approached it with a kind of dread. "I had examined the technical specifications," he wrote. "I had studied the engine, the fuel system, the control surfaces. Everything was straightforward, even crude by Japanese standards. But the numbers refused to make sense. The aircraft was too heavy to perform, as the instruments suggested it could. The engine was too powerful for carrier operations, or so I believed. I spent 2 days simply sitting in the cockpit, familiarizing myself with the controls, trying to reconcile what the gauges promised with what physics should allow." On July 23, 1943, Nakajima finally decided he was ready. The weather was clear, with light winds from the east. The runway at Lakunai was long enough barely for an aircraft as heavy as the Hellcat. Nakajima strapped in, performed his pre-flight checks, and signaled the ground crew. The R-2800 engine caught on the first attempt, settling into a deep and powerful rumble that Nakajima later described as unlike any aircraft engine I had ever heard, more like industrial machinery than aviation equipment. He let the engine warm up for 10 minutes, watching the oil temperature and cylinder head temperature gauges climb to operating range. Everything was stable. He tested the controls, ailerons, elevator, rudder, and found them responsive despite the aircraft's weight. Then he advanced the throttle for takeoff. His initial report, preserved in Japanese naval aviation archives and declassified in 1978, describes what happened next in the dry language of technical evaluation. Throttle advanced to takeoff power. Engine response is immediate and smooth, without hesitation or vibration. Acceleration rapid. Takeoff roll approximately 180 meters. Initial climb rate approximately 1,200 meters per minute at combat power setting. Aircraft handling conventional, though controls require more force than Zero or comparable Japanese fighters due to weight and control surface loading. But his personal diary, discovered by his family after his death in 1987 and donated to the Japanese Naval Aviation Historical Society, tells a different story. I advanced the throttle, expecting the hesitation, the vibration, the subtle signs of an engine being pushed to its limits. Instead, nothing, just smooth, continuous power, more power than I have ever felt in any aircraft. The Hellcat accelerated down the runway as if it weighed half what it actually did. When I pulled back on the stick, it climbed like a fighter half its size. I reached 3,000 meters in less than 4 minutes. I leveled off, and the indicated airspeed was 550 kilometers per hour faster than the Zero's maximum level speed. And the engine gauges showed I wasn't, even using maximum power. It occurred to me, alone in that cockpit over Rabaul, that we may have fundamentally misunderstood American industrial capacity. This isn't a prototype. This is production equipment. And if they can build engines like this at scale, then everything we've been told about American technical limitations is wrong. Over the next week, Nakajima conducted 14 test flights in the captured Hellcat. Each flight was designed to evaluate specific performance characteristics and compare them against known data for the Zero and other fighters. The results were methodical, thorough, and devastating. Test 3 evaluated turning performance. At low speeds, below 250 kilometers per hour, the Zero could indeed outturn the Hellcat. This was expected. The Zero's low wing loading and lighter weight gave it an inherent advantage in sustained turns. But Nakajima noted something crucial. The Hellcat didn't try to turn with the Zero. Its tactics would be different. Test 5 evaluated diving speed. Nakajima took the Hellcat to 6,000 meters, rolled inverted, and dove at full throttle. The indicated airspeed exceeded 700 kilometers per hour, a speed that would cause structural failure in a Zero. The Hellcat's controls remained responsive. The airframe remained solid. Test 7 evaluated combat durability. Nakajima fired the 650 caliber machine guns into a hillside target, measuring the recoil, evaluating the sight picture, assessing how long the aircraft could sustain fire. The result: approximately 20 seconds of continuous fire from all 6 guns. Compared to the Zero's 7.7mm guns, the difference in destructive power was profound. Test 9 was particularly revealing. Nakajima deliberately punctured one of the Hellcat's fuel tanks with a screwdriver, then observed what happened. Within seconds, the self-sealing compound had closed the hole. Fuel loss was minimal. In a Zero, the same. Puncture would mean fire and almost certain death. Test 12 evaluated the armor protection. Nakajima examined the armored seatback and the bulletproof windscreen. He calculated angles of protection and compared them to combat reports of Zero pilots being killed by rear attacks. The conclusion was obvious. The Hellcat pilot had protection the Zero pilot lacked. By the end of the test program, Nakajima had accumulated nearly 12 hours in the Hellcat. His final technical evaluation ran to 23 pages. The core findings can be summarized in a single paragraph from his report. The F6F Hellcat represents a fundamentally different approach to fighter design. It cannot outmaneuver the Zero in a turning fight at low speeds. However, it possesses superior speed in level flight and diving, superior climb rate, superior firepower, and superior survivability. American pilots trained to exploit these advantages while avoiding turning combat will possess a decisive tactical advantage. The Hellcat's performance suggests American industrial capacity to produce advanced engines at production scale far exceeds previous intelligence estimates. The report reached Combined Fleet Headquarters at Truk Lagoon in early August 1943. It was classified most secret and distributed to only the highest levels of Naval Aviation Command. What happened next reveals something profound about institutional inertia and the difficulty of accepting uncomfortable truths. Admiral Jisaburo Ozawa, commander of carrier forces for the Combined Fleet, read Nakajima's evaluation. He understood its implications. But he also understood something else. Japan couldn't build an answer to the Hellcat, not at the scale required, not with the materials available, not with the industrial capacity that was already stretched to breaking point. The philosophy of lightness, the strategy that had delivered early victories, had become a trap. Japan had optimized for a short, decisive war. They had built an air force, designed to win in 1941 and 1942. It was now 1943. The war had changed, and Japan's ability to adapt was constrained by resources, by industrial capacity, and by strategic decisions made years earlier that couldn't be reversed. Nakajima's report included a tactical recommendation: cease attempting to match American fighters in direct combat. Instead, emphasize the Zero's remaining advantages, superior low-speed maneuverability, and develop tactics that forced American fighters to fight on Japanese terms. It was sound advice, but it was also, in essence, a recommendation to accept defeat, just more slowly. Other captured Hellcats would follow. By late 1943, Japanese technical intelligence had examined at least 4 more examples, including one that had been shot down relatively intact near Bougainville. Each evaluation confirmed what Nakajima had reported. Each evaluation added more detail about American industrial capacity, about production techniques, about the growing technical gap, and each evaluation was read, acknowledged, and filed away as Japan continued building Zeros with minor modifications, continued training pilots for tactics that were becoming obsolete, and continued fighting a war that the material evidence suggested could not be won. The captured Hellcat at Rabaul remained at Lakunai airfield through late 1943. There are reports that Japanese pilots continued to fly it occasionally, using it to train fighter pilots in how to counter American tactics. But by January 1944, Allied bombing of Rabaul had intensified to the point where the airfield was under almost constant attack. Records suggest the Hellcat was destroyed in a bombing raid on January 23, 1944, though some reports indicate it may have been deliberately burned by Japanese forces during the evacuation of Rabaul in February. Either way, its technical intelligence had already been extracted, analyzed, distributed, and ultimately unable to change the course of events. What the captured Hellcat revealed wasn't just about horsepower or armament. It was about the industrial chasm opening between Japan and the United States. and the numbers tell that story with brutal clarity. In 1943, Grumman produced 2,545 Hellcats. Japan produced 1,854 Zeros. But that ratio doesn't capture the real disparity. Each Hellcat required more raw materials, more machine hours, more advanced components than a Zero. Japan was already operating at maximum industrial capacity. America was just getting started. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By 1944, the production gap had become a chasm. Grumman built 6,139 Hellcats that year. Japan built 2,330 Zeros. And by then, American factories were also producing thousands of P-51 Mustangs, P-47 Thunderbolts, and F-4U Corsairs, each with engines producing 2,000 horsepower or more. The philosophy of lightness, which had seemed so brilliant in 1941, was drowning in American steel. But the real impact of the Hellcat wasn't just technical, it was psychological. Saburo Sakai, who survived the war as one of Japan's highest-scoring aces, wrote about this shift in his memoir, published in 1957. "We had been told we flew the finest fighter in the world. We believed it because our experience proved it true. We could outturn any American fighter. We could outclimb them. In the first year of the war, we owned the sky." But after mid-1943, something changed. American fighters, first the Hellcat, then others, stopped trying to dogfight us. They would dive from above, fire, and climb away before we could respond. Again and again, we could not catch them. We could not force them to fight on our terms. The Americans had learned, and they had given their pilots machines that made their new tactics possible. We still had skill. We still had courage. But skill and courage were not enough against an enemy who could simply refuse to fight except on their own terms. This was the real revolution the Hellcat represented. It wasn't just a better fighter. It was a fighter that enabled a completely different approach to air combat. American fighter tactics evolved rapidly after 1943, driven by combat experience and systematic analysis of what worked. The doctrine became known as boom and zoom, use altitude advantage and superior speed to attack, deliver a high-speed firing pass, then climb away before the Zero could maneuver into position for a counterattack. The Hellcat made this possible. Its R-2800 engine gave it superior climb rate, allowing it to regain altitude advantage quickly. Its diving speed exceeded anything Japan could field. Its armor meant pilots could survive mistakes. A deflection shot that would kill a Zero pilot might leave a Hellcat pilot wounded but alive, able to return to his carrier. And the Hellcat's combat record reflects this tactical revolution with devastating clarity. By the end of 1943, the kill ratio had shifted. Hellcats were destroying Japanese aircraft at a ratio of approximately 6-1. By mid-1944, during the Battle of the Philippine Sea, the engagement American pilots nicknamed the Great Marianas Turkey Shoot Hellcats achieved kill ratios exceeding 19-1. That isn't a typo. 19 Japanese aircraft were destroyed for every Hellcat lost in air combat. The final tally, compiled after the war, shows that Hellcats were credited with destroying 5,223 enemy aircraft, more than any other Allied fighter type. Only 270 Hellcats were lost in air-to-air combat during the entire war. Japanese pilots who survived the war later described the psychological impact of facing Hellcats with a kind of bitter clarity. In interviews conducted decades after the war ended, when the emotions had cooled and honest assessment became possible, they spoke about the creeping sense of inevitability that set in after 1943. One veteran, speaking in a 1989 oral history interview preserved at the Japanese Naval Aviation Historical Society, put it this way: "We still had skill. We still had courage. We could still outturn American fighters if we could force them into a dogfight. But they wouldn't fight us on our terms anymore. They had learned. And more than that, they had given their pilots machines that made it possible to refuse our challenge. You cannot dogfight an economy, you cannot outturn industrial production, and by 1944, we understood that this was what we were really fighting. The captured Hellcat that Lieutenant Commander Nakajima flew in July 1943 should have been a warning. In some ways, it was. His report was accurate, detailed, and clear about the implications. But institutional momentum is a powerful force. Japan couldn't simply redesign its entire aviation industry in response to one captured aircraft, no matter how alarming its capabilities. They tried to respond. The A7M Repu was designed as a zero successor, incorporating some of the lessons learned from examining captured American fighters. It would have been an excellent aircraft, but only 9 were completed before the war ended. Materials shortages, bombing of factories, and the simple fact that development takes time meant that Japan's response to the Hellcat arrived too late and in numbers too small to matter. The J-2M Raiden Interceptor was another attempt, a high-speed, heavily armed fighter designed specifically to counter American bombers and their fighter escorts. But production was plagued by engine problems and materials shortages. Only 476 were completed. Meanwhile, American production continued accelerating. Hellcats, Corsairs, Mustangs, Thunderbolts, thousands upon thousands. Each month, an unstoppable tide of aircraft powered by engines that Japanese engineers had initially refused to believe were real. There's a document in the United States Strategic Bombing Survey, compiled after the war by American investigators who interviewed Japanese engineers and military officials, that reveals something profound about Japan's understanding of the technical gap. American investigators asked Japanese aviation engineers why Japan hadn't developed more powerful engines comparable to the R-2000-800 or the Allison V-1000-710 or the Rolls-Royce Merlin. The answers were revealing. First, materials. High-grade alloy steels required for advanced engines simply weren't available in sufficient quantities. Japan lacked access to the chromium, molybdenum, and nickel necessary for engine components that could withstand extreme heat and stress. Second, machine tools. Manufacturing precision engine components required machine tools that Japan hadn't imported in sufficient numbers before the war and couldn't manufacture domestically at the scale required. Third, fuel. Testing and developing high-powered engines required high-octane aviation fuel. By 1943, Japan was already facing fuel shortages that limited training for pilots, let alone extended engine testing programs. But there was also something else in those post-war interviews, something that reveals how deeply the philosophy of lightness had become embedded in Japanese aviation thinking. Even in 1945, with the war lost and Japanese cities burning, some engineers insisted that extremely high-powered engines were wasteful, inefficient, and unsuitable for carrier operations. They argued that the American approach, brute force through massive engines, was technically inferior to the Japanese philosophy of achieving maximum performance through minimum weight. They had confused a beautiful idea with a winning strategy. They had mistaken elegance for effectiveness. This is the deeper tragedy of the story. It wasn't that Japanese engineers were incompetent. The Zero was a genuine masterpiece of aeronautical engineering, a triumph of doing more with less. But mastery of one approach to a problem doesn't guarantee victory when your opponent is solving a different problem entirely. Japan optimized for a war that would be decided by pilot skill and aircraft maneuverability in close-quarters dogfights. America built for a war that would be decided by industrial capacity and the ability to give adequate pilots overwhelming material advantages. Both approaches were rational. Both were based on reasonable assumptions, but only one matched the reality of what the Pacific War became. Tadashi Nakajima survived the war. After his test flights of the Hellcat in 1943, he returned to combat duties, flying defensive patrols over Rabaul through early 1944. He was then reassigned to training duties in Japan as experienced pilots became too valuable to risk in frontline combat. His 1952 memoir, Memoirs of a Test Pilot, is a slim volume, out of print in Japan, and never officially translated into English. But aviation historians who have read it describe it as brutally honest about the technical gap between Japanese and American aviation by the middle years of the war. In one passage, Nakajima reflects on that first flight in the captured Hellcat. I remember looking at the fuel gauge, at the oil pressure gauge, at the manifold pressure, all reading normal despite delivering power I had not believed possible in a production aircraft. And I remember thinking, how many of these do they have? That question haunted me for the rest of the war. Not just how many Hellcats, but how many of everything. How many carriers could produce that much steel? How many factories could manufacture those engines? How many pilots could they train to fly them? How much fuel did they have to support operations at this scale? The answer, I eventually understood, was more than we could destroy. Always more than we could destroy. Nakajima never personally flew in combat against Hellcats. He was transferred to training duties before they became common in his operational area, but he trained young pilots who would face them. He tried to teach them the tactics that might give them a chance. Never dogfight, never let the American pilot dictate the engagement, use surprise and aggression. But I also knew, he wrote, that I was teaching them how to survive, not how to win. There is a difference. Survival tactics are what you teach when victory is no longer possible. You teach them to last as long as they can, to take as many of the enemy with them as possible, and to accept that the final outcome is already determined. Nakajima worked in Japan's civil aviation industry after the war, helping rebuild commercial air transport in a country where aviation had been banned by occupation authorities until 1952. He rarely spoke publicly about his wartime service, but he gave one interview in 1978 to a Japanese aviation history magazine where he was asked specifically about the Hellcat test flights. It was the moment I understood we would lose, he said. Not because of that one aircraft, but because of what it revealed about the gap between our industrial capacity and theirs. We were fighting with different resources, different capabilities, different realities. In that cockpit, with my hand on that throttle, I could feel the weight of American industry. 2,000 horsepower was just a number, but what it represented, the materials science, the manufacturing precision, the industrial capacity to produce thousands of these engines was unstoppable. We had built the most elegant fighter in the world. They had built the most effective. And in war, effectiveness defeats elegance every time. The Grumman F6F Hellcat served with distinction through the end of the war. It participated in every major carrier battle from late 1943 through August 1945. It covered the landings at Tarawa, Saipan, the Philippines, Iwo Jima, and Okinawa. Its pilots shot down the last Japanese aircraft destroyed in air combat 3 A6M0s over Tokyo Bay on August 15, 1945, hours after Japan had announced its surrender. After the war, most Hellcats were scrapped or sold as surplus. A few served in other nations' air forces. France used them in Indochina. Argentina and Uruguay operated them into the 1960s. Some became civilian air racers. Most were simply melted down, their aluminum recycled into the consumer goods of peacetime America. Today, fewer than 20 Hellcats still fly. Perhaps 50 more sit in museums around the world, preserved as examples of the aircraft that helped win the Pacific War. There's a Hellcat on display at the National Air and Space Museum in Washington. It's painted in the markings of Fighting Squadron 2, the Rippers, and it's suspended from the ceiling in a steep dive, frozen in the moment of attack. Near it, not close, but visible in the same gallery, is a preserved Zero. Even decades after the war, even motionless in a museum, the contrast is obvious. The Zero looks graceful, almost delicate. The Hellcat looks brutal, purposeful, designed for a job rather than for beauty. Visitors photograph both. School groups walk beneath them. Most don't know the technical specifications or the combat records, but they can see the difference in design philosophy just by looking. The story of Japanese pilots refusing to believe the Hellcat's engine specifications is often told as a moment of Japanese naivete, a punchline about technological denial. But that's the wrong lesson entirely. The tragedy isn't that Japanese engineers couldn't believe 2,000 horsepower was real. The tragedy is that they understood exactly what it meant, reported it accurately, and watched as institutional momentum, strategic commitments, and material limitations prevented Japan from responding effectively. They had built an air force optimized for the wrong war. Not because they were foolish or technically incompetent, the Zero was a masterpiece of aeronautical engineering, arguably the finest lightweight fighter ever designed. But because they had made assumptions about what kind of war they would fight, how long it would last, and what resources would be available, those assumptions were wrong. And by the time the evidence became undeniable, it was too late to change course. The Hellcat didn't win the Pacific War by itself. No single weapon system ever does. Wars are won by logistics, by industrial capacity, by training systems, by strategic vision, by 10,000 factors that interact in complex ways. But the Hellcat represented a fundamental truth about modern warfare that Japan couldn't counter. Industrial capacity, given time, defeats elegance. Production trumps perfection. A nation that can build thousands of effective weapons will defeat a nation that builds hundreds of perfect ones. Lieutenant Commander Tadashi Nakajima understood this in July 1943, sitting alone in a cockpit on a distant airfield, his hand on a throttle that delivered impossible power. He understood it, he documented it in his report, he communicated it to his superiors, and then he watched as the war continued anyway, grinding toward its inevitable conclusion, while Japanese factories continued building Zeros, beautiful, elegant, inadequate Zeros because there was nothing else they could do. The gauges in that Hellcat cockpit weren't lying. They never were. The manifold pressure was real. The horsepower was real. The industrial capacity that made it possible was real. The question was never whether the instruments were accurate. The question was whether Japan could accept what those instruments were telling them, and whether they had the time and resources to do anything about it. The answer to both questions was no. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now, and don't forget to subscribe. The morning of June 9th, 1944, SS Panzer Grenadier Adolf Morawetz sits inside his Panther tank, turret number 312, watching the French countryside through his periscope. The air inside smells of diesel fuel, gun oil, and the sweat of 5 young men crammed into a steel box. 3 days after the Allied invasion at Normandy, his company received orders to retake the village of Nory-en-Bessin from the Canadian forces who held it. Morawetz feels something close to confidence. His Panther is supposed to be invincible. The mathematics are clear. 80 millimeters of frontal armor, angled at 55 degrees, providing protection equivalent to 139 millimeters of vertical steel. The Americans cannot touch it from the front. Their 75-millimeter guns bounce off like stones thrown at a fortress wall. Even the British 6-pounder anti-tank gun, which had performed well in North Africa, can barely scratch the paint at combat ranges. His Company 12 Panthers from the 12th SS Panzer Division rolls toward Norry at 1300 hours. They approach in 2 columns, engines roaring, tracks churning the Norman soil into twin furrows of devastation. The plan is simple, the kind that has worked before. Overwhelm the Canadian position with superior firepower and armour. Standard Panzer doctrine. Textbook tactics. At 1,000 metres from the village, the Canadian tanks open fire. The first thing Morawetz notices is the sound. Not the familiar crack of a 75mm Sherman gun, something deeper, sharper, like the tearing of metal at its molecular level. His Panther shudders. For half a second, he thinks they have struck a mine. Then comes the second impact. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ammunition for the MG-42 machine gun ignites inside the crew compartment. Flames erupt through the confined space where 5 men work in coordinated rhythm. Through his periscope, in the half-second before he desperately claws at the hatch above his head, Morawetz watches the Panther beside his own explosion. The entire turret lifts into the air like a child's toy thrown in anger, spinning as it rises before crashing back to Earth 30 meters away. In the next 4 minutes, 7 of the 12 Panthers are destroyed. The survivors retreat in disorder, leaving Nory-en-Bessin firmly in Canadian hands. Morawetz survives. His tank and most of his crew do not. The bodies were recovered 3 days later, burned beyond recognition. What happened in those 4 minutes would become a pattern that repeated across the Norman countryside throughout the summer of 1944. The Canadians had not been firing regular Sherman guns. They had been firing something the Germans had not expected to encounter in such numbers, the British 17-pounder anti-tank gun, mounted in specially modified Sherman tanks that Allied crews called Fireflies. And at 1,000 metres over half a mile, the 17-pounder could penetrate straight through a Panther's frontal armour as if the steel were paper. This is the story of how the most feared German tank of World War II met the weapon that transformed it from an instrument of terror into what Panther crews themselves came to call a suicide machine. It is a story about the collision between technological confidence and material reality, about the mathematics of armour penetration and the psychology of men who discovered their protection was an illusion. To understand how profound this shift was, you must first understand what the Panther represented to the men who crewed it. By June of 1944, Panther crews had earned their confidence through experience and engineering. The Panzer V Panther tank was born from Germany's traumatic encounter with the Soviet 34 in 1941. German tank crews on the Eastern Front had watched with growing horror as their Panzer IIIs and IVs were consistently outmatched by Soviet tanks with sloped armour and powerful guns. The psychological impact cut deep enough that designers received emergency orders to create something superior immediately. The result combined the sloped armour concept of the 34 with German engineering precision and a devastating 75mm KAK 42L70 gun. That gun could penetrate 139 millimeters of armour at 1,000 meters. Its high muzzle velocity and accuracy made it lethal at ranges where Allied tanks could not even respond effectively. The frontal armour proved equally impressive in testing and combat. The 80mm upper glacis plate, sloped at 55 degrees, was effectively impervious to most Allied tank guns when struck from the front. American 75mm shells simply bounced away, leaving only scratches. The British 6-pounder anti-tank gun, which had performed admirably against earlier German tanks in North Africa, could barely damage it at normal combat ranges. Heinz Guderian, one of Germany's most respected panzer commanders, published tactical recommendations for Panther battalions that emphasized this technological advantage. Engage at long range 1,500 to 2,000 meters, where the Panther could destroy enemy tanks with near impunity, while remaining invulnerable to return fire. Never present the sides or rear. Spread out platoons to maximize overlapping fields of fire. Maintain reserves 1 kilometer behind the front line to cover the flanks. It was doctrine built entirely on the assumption of technological superiority, and for the first year of the Panther's service life, from its combat debut at Kursk in July 1943 through the spring of 1944, that assumption held true often enough to sustain confidence. When Allied planners prepared for the Normandy invasion in early 1944, they committed a critical intelligence failure. They knew about the Panther. Soviet intelligence had provided technical details after capturing examples on the Eastern Front. The tank had been encountered in small numbers by Allied forces in Italy, but American and British intelligence analysts made a catastrophic assumption. They believed the Panther would remain a rare heavy tank, produced in limited quantities like the Tiger, deployed only in elite formations for specific missions. They were wrong by an order of magnitude. By the 6th of June, 1944, Germany had produced thousands of Panthers. Production had reached approximately 380 units per month by May of that year. In the Normandy sector, 38% of all German tanks were Panthers. For American units, equipped with standard 75mm Sherman tanks, this represented a tactical disaster of the first order. The standard M4 Sherman, armed with the 75mm gun, could not penetrate a Panther's frontal armour at any practical combat range. Crews had to close to within a few hundred meters and aim for specific weak points: the thinner side armour, the rear engine deck, the gun mantlet if the angle was perfect. That meant closing to ranges where the Panther's 75mm gun could destroy a Sherman with a single hit through the frontal armour. American tank crews developed mathematics of survival that were simple and brutal. It took 5 Shermans to destroy 1 Panther. 4 of those Shermans would burn. Their crews would die. The 5th might succeed if it could maneuver to the Panther's flank while the German crew was distracted by killing the first 4. These were not theoretical calculations. They were observations drawn from actual combat in the weeks following D-Day. Crews learned them by watching friends burn to death in tanks that were supposed to protect them. By late June of 1944, after experiencing the reality of Panther engagements across multiple sectors, General Dwight Eisenhower was furious enough to demand immediate action. He ordered comprehensive penetration tests of all Allied guns against captured Panther hulls. The testing occurred at multiple locations using actual battlefield conditions and ammunition. The results confirmed what tank crews already understood from direct experience. American guns were catastrophically inadequate against the Panther's frontal armour. The 75mm gun could not penetrate frontally at any range. The new 76mm gun, which had been rushed into service specifically to address German armour improvements, was better, but only marginally so. It could penetrate the Panther's mantlet at 500 yards if the angle was favourable, but it could not defeat the glacis plate even at point-blank range. The Americans had one weapon system that could handle Panthers effectively: the M36 tank destroyer, armed with a 90mm gun. But the M36 did not arrive in Europe in meaningful numbers until September of 1944. For the critical months of June, July and August, the entire Battle of Normandy, American armoured forces were consistently outgunned when facing Panthers. But the British had pursued a different path. While American planners had remained sceptical about the scale of the Panther threat, The British were paying very close attention. After spending 2 years catching up to German tank development in North Africa, watching their tank designs consistently prove inferior in combat, they were determined not to fall behind again. The experience of being outmatched had been psychologically devastating and tactically costly. Development of the 17-pounder anti-tank gun had begun in late 1940, before the Panther even existed as more than preliminary sketches. British designers correctly anticipated that German armour would continue to thicken, that each new tank design would be harder to defeat than the last. They needed a gun that could handle whatever came next, not just what existed now. The 17-pounder, actually a 76.2mm gun that fired a projectile weighing 17 pounds, emerged from this forward-thinking design philosophy. When the first prototype 17-pounders were rushed to North Africa in early 1943 to counter the Tiger I heavy tank, they were so urgently needed that they arrived before proper carriages had been manufactured. These emergency weapons were mounted on 25-pounder gun howitzer carriages, creating improvised hybrid weapons that Allied troops nicknamed pheasants. They worked. The 17-pounder could penetrate a Tiger's frontal armour from 1,000 yards using standard ammunition. This was a revelation to crews who had been struggling with inadequate 6-pounder guns. But the British faced a structural problem that threatened to waste this technological advantage. They did not have a tank capable of mounting the 17-pounder. British tank designs, like the Cromwell and Challenger, were either not ready for production or physically incapable of accommodating such a large gun. The Challenger tank, specifically designed around the 17-pounder, experienced constant delays and mechanical problems. The Cromwell's turret ring was too small. The solution came from an unexpected source: 2 persistent British officers who proposed mounting the 17-pounder in the American-supplied Sherman tank. On paper, the idea appeared impossible. The 17-pounder was enormous. Its breech alone was massive, requiring significant space behind the gun. The barrel extended over 13 feet. The Sherman's turret had been designed for the much smaller 75mm gun. Nothing about the Sherman's internal geometry suggested it could accommodate a weapon 50% more powerful. Initial proposals were rejected by the Ministry of Supply. The technical challenges seemed insurmountable. But through a combination of bureaucratic persistence and connections with influential officers who understood the tactical necessity, the project received official approval in late 1943. Engineer W.G.K. Kilbourne solved the seemingly impossible technical challenges through a series of clever compromises. The gun was mounted on its side rather than upright, changing the recoil geometry. The turret was modified with new internal bracing. The co-driver's position was completely eliminated, and that space was converted to ammunition storage for the massive 17-pounder shells. The radio operator took over the bow machine gun. The crew was reduced from 5 to 4 men. The result was awkward, cramped, and mechanically brilliant. The Sherman Firefly, as it came to be called, mounted one of the most powerful anti-tank guns in the world on a reliable, mass-produced chassis that Allied supply chains already supported completely. By the 6th of June, 1944, 342 Sherman Fireflies were ready for deployment with British and Canadian forces landing in Normandy. Production accelerated rapidly. By the end of August, over 550 Fireflies had been delivered. British and Canadian armoured regiments were equipped with 1 Firefly per troop of 4 tanks. The ratio was low, only 25%, but it proved sufficient. Because the 17-pounder could accomplish something no other Allied tank gun could, it could kill a Panther from the front at normal combat ranges. The British War Office conducted systematic penetration testing against captured Panthers throughout 1944. The data was compiled into classified intelligence reports and distributed to tank crews and unit commanders. The numbers told a story that would fundamentally alter the tactical calculus of armoured warfare in Northwest Europe. Using standard armour-piercing, capped, ballistic-capped ammunition, the kind available in quantity, the kind crews could rely on receiving regularly. The 17-pounder could penetrate 130 millimeters of armour at 500 meters, and 119 mm at 1,000 meters, when striking at a 30-degree angle from vertical. Against a Panther's 100 mm gun mantlet, even when that mantlet was struck at an angle, the 17-pounder achieved reliable penetration from ranges exceeding 2,500 yards. Against the Panther's side armor, penetration was essentially guaranteed at any combat range. The sides were much thinner than the front, protected by only 40 mm to 50 mm of vertical steel. The 17-pounder could penetrate this thickness from well over 2,000 yards, but the 17-pounder possessed a special type of ammunition that pushed penetration performance into a different category entirely. Armor-piercing discarding sabot rounds used a dense tungsten core, much smaller than the gun's caliber, surrounded by a lightweight aluminum sabot that fell away after leaving the barrel. The small, heavy penetrator achieved extraordinary velocity and therefore extraordinary penetration. APDS ammunition could penetrate 209 mm of armor at 500 meters and 192 mm at 1,000 meters when striking at a 30-degree angle. This meant the 17-pounder firing APDS could theoretically penetrate even the front of a King Tiger heavy tank at combat ranges. Against a Panther, it was absolutely devastating. British intelligence analysis confirmed that APDS could penetrate a Panther's frontal glacis armor from 1,500 meters. There was a significant problem with APDS that limited its tactical usefulness. The ammunition was horrifically inaccurate compared to standard rounds. The sabot's separation from the penetrator after leaving the muzzle caused unpredictable flight characteristics. At a test range under absolutely ideal conditions with experienced gunners, APDS achieved only a 20% hit rate at 800 yards. In field trials against a captured Panther, experienced gunners firing dozens of rounds at ranges between 200 and 600 yards achieved roughly 50% accuracy. Beyond 1,000 yards, the accuracy degraded so severely that test firers at British ranges frequently could not hit a stationary Panther-sized target at all, even after multiple attempts. So Firefly crews used APCBC as their standard combat ammunition. It was accurate enough to hit targets reliably at 1,500 to 2,000 meters. And it was powerful enough to penetrate Panthers frontally at 1,000 to 2,000 meters, exactly the ranges where German doctrine said Panthers should be invulnerable. APDS was kept in reserve for close-range emergencies, for situations where absolute penetration was needed immediately, and accuracy mattered less because the target was close enough to hit reliably. The psychological impact of this capability on Panther crews cannot be overstated. For the first time since the Panther entered service, there existed an Allied weapon that could kill them at the ranges German tactical doctrine considered safe. The fundamental assumption underlying Panther tactics that frontal armor provided protection at long range was no longer true. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. 8 days after the engagement at Nory-en-Bessin, another confrontation demonstrated the tactical lethality of properly employed fireflies. Sergeant Harris of the 4th 7th Royal Dragoon Guards commanded a Sherman Firefly near the hamlet of Comparitidi, Lingevres, close to Tilly-sur-Sulz. His gunner was Trooper MacKillop, a Scottish soldier known both for exceptional marksmanship and for a personal philosophy about ammunition that his crewmates found amusing. MacKillop hated wasting shells. 5 Panthers from an unidentified German unit approached along a narrow road, moving at moderate speed. The crews appeared confident, unaware that a Firefly lay in concealment roughly 1,000 meters distant. Sergeant Harris waited, calculating range, wind, and the optimal moment. The Panthers continued their approach. Turrets traversed forward, maintaining formation. At approximately 1,000 meters, MacKillop fired the first round. The lead Panther exploded, flames erupting from hatches as ammunition cooked off. The second Panther was struck before its crew could react to the first tank's destruction. The third Panther attempted to reverse, but the driver's panic made the maneuver clumsy, and MacKillop's third round penetrated the frontal armor while the tank was stationary. The fourth Panther, turned to present its side, a catastrophic tactical error, born of confusion, and was destroyed by the fourth round. The fifth Panther managed to begin a retreat, but McKillop's final shot caught it before it reached concealing terrain. 5 Panthers destroyed, 5 rounds fired, 5 hits. The engagement lasted less than 5 minutes from first shot to the destruction of the final target. Harris and McKillop repositioned their Firefly twice during the action, using terrain features to maintain concealment and prevent German artillery observers from fixing their location. This was textbook Firefly doctrine. Exploit the gun's range advantage, strike from concealment, move immediately after firing to prevent counterfire, strike again from a new position. German after-action reports from units operating in that sector during mid-June noted devastating long-range British anti-tank fire, but struggled to understand what weapon system was being employed. Some reports incorrectly attributed kills to towed anti-tank guns rather than tanks, because German doctrine held that no Allied tank gun could achieve such performance at those ranges. This confusion was not accidental. British command had issued explicit orders that Firefly crews must camouflage their tanks to disguise the distinctive long barrel. Crews wrapped the barrel end with foliage, painted counter-shading patterns to break up the gun's outline, and avoided exposing their silhouette unnecessarily. The Germans had learned quickly to prioritize Fireflies once identified, directing concentrated fire from tanks and anti-tank guns toward any Sherman with a long barrel. But camouflage could not hide the fundamental tactical reality. Any time a Firefly could see a Panther, the Firefly could kill the Panther. And Panthers could no longer rely on armor for protection at long range. On July 8, 1944, during Operation Charnwood, a major British offensive to capture the city of Caen, the village of Buron, became the site of one of the most successful anti-tank engagements of the entire Normandy campaign. The battle demonstrated both the lethality of the 17-pounder and the tactical problems German armoured units now faced. A mixed force of Panzer IVs and Panthers from the 12th SS Panzer Regiment launched a counterattack against Canadian infantry positions south of Buron. The German plan followed standard counterattack doctrine: use armoured mass to disrupt enemy offensive operations, drive the infantry back, restore the defensive line. The tanks advanced with infantry support, moving across relatively open ground toward prepared Canadian positions. They encountered B Troop of the 245th Battery, 62nd Anti-Tank Regiment, Royal Artillery. The unit had been attached to the Royal Hamilton Light Infantry to provide anti-tank support. Their equipment consisted of both towed 17-pounder, anti-tank guns and M10 Achilles self-propelled guns, modified American M10 tank destroyers that had been rearmed with 17-pounders instead of their original 3-inch guns. The engagement was brief and catastrophic for the German armoured force. 13 German tanks were destroyed, a mix of Panthers and Panzer IVs. British losses included 4 self-propelled guns destroyed and 4 more damaged, but the German counterattack was completely shattered. The German infantry, without armoured support, could not continue the attack and withdrew. British gun crew accounts describe firing in rapid succession at ranges between 800 and 1500 metres. The terrain south of Buron provided excellent fields of fire across relatively flat, open ground. German tanks attempting to close with the Canadian infantry positions found themselves completely exposed to devastating anti-tank fire from prepared positions that the advancing tanks could not effectively suppress. For Panther crews, this type of engagement represented the collapse of their tactical doctrine. The open terrain that should have favoured their superior long-range firepower instead exposed them to equally long-range Allied guns that could penetrate their armour. The numerical advantage they expected more Panthers than Fireflies in most engagements did not matter when every 17-pounder position could destroy any tank it could see. The armoured doctrine that had sustained German tactical confidence was becoming a death sentence. Not all terrain favoured the Fireflies' advantages. The hedgerow country of Normandy, the dense bocage, created tactical conditions that negated many of the 17-pounders' strengths and created new vulnerabilities for both Panthers and Fireflies alike. General Fritz Bayerlein, commander of Panzer Lehr Division, filed reports noting that the Panther performed poorly in bocage terrain. The long gun barrel severely reduced maneuverability on narrow lanes between high hedgerows. The tank's weight distribution, front-heavy with the engine in the rear, made it difficult to traverse steep embankments. The crew's vision was restricted by the high hedges, making them nearly blind to infantry approaching from the sides. The Firefly suffered nearly identical problems. Its barrel was actually longer than the Panther's over 13 feet, compared to roughly 11 feet for the Panther's main gun. In confined spaces between hedgerows, both tanks struggled to maneuver without exposing vulnerable side armor, and the Firefly's powerful long-range gun became almost useless when engagement ranges measured in tens of meters rather than hundreds. Close-quarters combat in villages and dense bocage favored neither tank design. Both were vulnerable to infantry anti-tank weapons, British Piites, German Panzerfausts, American bazookas. Both could be destroyed by well-positioned anti-tank guns firing from ambush at near point-blank range. In these conditions, crew training, tactical awareness, and simple luck mattered more than technical specifications. The engagement at Chio on June 27th demonstrated these dynamics clearly. 6 Panther tanks from an SS unit moved through orchards and sunken lanes approaching British positions held by the 5th Duke of Cornwall's light infantry. The terrain prevented long-range engagements. Visibility was measured in dozens of meters, not hundreds. British infantry attacked the Panthers with PIAT anti-tank launchers at extraordinarily close range. Sergeant Hicks disabled the 1st Panther with multiple Piat hits, beginning his attack from 100 yards and closing to 10 to 15 yards for the final disabling shot. Captain Blackwell stalked a 2nd Panther unseen by the German crew and fired his Piat from only 10 yards away, disabling the tank before the crew could react. The infantry attacks confused the German crews and, critically, bought time for British anti-tank gunners, who were attempting to bring a 6-pounder gun into position roughly a quarter-mile to the rear. When the gun crew, Sergeant Wilson, Corporal Bryce, and Private Elliott finally had their weapon positioned and ready to fire, 3 Panthers had pushed into an orchard approximately 400 yards away. The gun engaged all 3 Panthers in rapid succession, destroying them with 11 rounds total. Lieutenant Colonel Atherton was killed during this action while assisting the crew as a loader, replacing a casualty. Private Elliott later described the engagement as a terrific scrap, noting that the Panthers were difficult targets because they were approaching head-on and were partially concealed by trees. 4 of the 6 Panthers were destroyed in the engagement. The remaining 2 were damaged and withdrew. The action demonstrated that in close terrain, neither Panther armor nor Firefly firepower guaranteed victory. Crew courage, tactical flexibility, and the ability to coordinate between infantry and anti-tank assets determined outcomes. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.